Microphone working? Good. Because we're mixing two sources of audio here, so I hope it works okay. It's a great pleasure to be here. Originally, I was asked to come a year ago, and I couldn't come last year, but I committed to this date, thinking that I could do a backcountry ski trip with my wife. But you know what the snow conditions are like, so that hasn't worked out. But still, it's wonderful to be here in Seashell. And thank you for inviting me. And I really enjoyed the star this month, the sky this month. I learned a huge amount that I didn't know about Milankovitch cycles and the fact that the winter and summer are different lengths. I had no idea, so it was worth it just for that. Okay, so I'm here actually to talk about something quite different. I'm going to talk about supernovae and the mystery of dark energy. And in this talk, I'm going to talk somewhat about supernovae, stars that explode. I'm going to talk about dark energy and cosmology, but I'm also going to talk about telescopes. And I thought that I would start off by telling you a little bit about the telescopes that we used in this project. So let's just get this started. This was supposed to be a supernova. As you know, there's sound in outer space, so this is what happens when a supernova explodes. I think there's going to be a big bang, so prepare for it. There it goes. That's a supernova explosion. And if you didn't know that it was a supernova explosion, you could tell from the sound. But what I'm going to talk about first is actually the telescopes that we used in this project. And as you probably know, some of the best telescopes in the world are located on the big island of Hawaii, which is shown in this picture. How many people here have been to the big island of Hawaii? Quite a few people. How many of you have seen the telescopes up close? Wow, fantastic. So this is what the summit of Mauna Kea, 4,000 meters high, looks like at the present time. There was a big snowstorm 2 nights ago, and actually the summit is completely shut down. It's not possible to get there. And that is critical for one reason. There's a telescope that is going to start construction, was going to start construction this week, that Canada is involved with, the 30-meter telescope. But unfortunately, because of the snowstorm, they weren't able to start construction. And I hope after the talk is over, some of you ask me about the 30-meter telescope, because there's quite a story to tell you there. It's going to be one of the world's largest telescopes. 30 meters in size is like the width of a football field. And this is an optical telescope. So it's going to be absolutely immense. It's going to be a marvelous telescope. But enough about the 30-meter telescope. This is what the summit of Mauna Kea looks like. On a good day, you can see all the telescopes. This is a somewhat dated picture, but we are involved. Canada is involved with 3 of the telescopes that you see here. The Canada-France-Hawaii telescope, one of the first telescopes on the mountain. Gemini North, we're 20% partners in Gemini North, and we were involved with the James Clerk Maxwell telescope, although that has changed now. Unabashed advertising for a friend of mine, Jean-Charles Cleandre. This is a trailer for a movie that he produced. Just 1 minute. That film is actually available on Amazon.com. Unfortunately, not on Amazon.ca. But if you want to see it at low resolution, It's available on YouTube as well, so I suggest you check it out. Hawaiian started it. Again, these are the two telescopes that we used for our project, the 8-meter Gemini North telescope and the 3.6-meter Canada-France Hawaii telescope. And I'm going to tell you a bit more about the observations that we made a little later in the talk. But what I'd like to do now is move on from telescopes and talk a little bit about cosmology, the origin of the universe. I think the beginning of modern cosmology was in 1915. It was Einstein, person of the year for the person of the century for the 20th century. What Einstein did in 1915 was come up with a theory of general relativity. And what this theory says is that gravity actually is caused by the curvature of space-time. It seems like a really odd concept, but in fact, that theory has been verified in countless experiments. And I don't have time to tell you about the experiments that have verified general relativity, but they've been absolutely remarkably precise and confirming of his theory. But one thing that Einstein realized early on was that the universe, if it were just sitting there in general relativity, it would either collapse or have to be expanding. It would have to be a dynamic universe. Either the universe would collapse under its own gravity, or else it would have to be expanding to counteract that tendency to collapse. Einstein did not like that. He didn't know anything about an expanding universe. He thought that the universe would have to be static. And so what he did was he invented something called the cosmological constant to add to his equations, his very complicated equations. Even though they're complicated, all they say is that the source of gravity is equal to the curvature of space, or space-time. He added in this large-scale repulsive force in the universe to counteract gravity. And by doing that, he was able to make a universe that was completely static. And that's where things rested for about 13 or 14 years, until 1929, when Hubble announced his discovery of the expansion of the universe. Really, the expansion of the universe was discovered by someone by the name of Vesto Slipher back in the early 20s. Vesto Slipher actually discovered that galaxies were moving at very high velocities away from the Milky Way. But it was Hubble that systematized all this knowledge in his paper and showed that the universe as a whole was expanding. And so Einstein basically had made a mistake. If he hadn't introduced the cosmological constant, he would have predicted the expansion of the universe, which would have been the greatest triumph of all of physics, I think it's fair to say. As it was, he introduced the cosmological constant and missed predicting the expansion of the universe theoretically. And in fact, there's this beautiful quotation in a wonderful book by George Gamow, My World Line. It's basically George Gamow's autobiography. It says, much later, when I was discussing cosmological problems with Einstein, he remarked that the introduction of the cosmological term was the biggest blunder of his life. So what a blunder, or was it a blunder? We're going to come back to that. So very soon after Hubble discovered the expansion of the universe, it was realized by Hubble and by others. But what this meant was that there was a Big Bang from where everything came from. He didn't call it the Big Bang. I think that was Fred Hoyle that called it the Big Bang. But after the Big Bang, the universe would expand. And then what would happen to the universe? Well, the universe might expand forever, or the universe might eventually halt its expansion and collapse back down to, I guess you could call it a big crunch. What would determine those two things? Well, it's sort of like taking a tennis ball, which is why I have a tennis ball here. You know that if I throw this tennis ball up in the air, unfortunately I caught it, Gravity causes the tennis ball to stop its motion and fall back down. But you know that if you throw the tennis ball fast enough or hard enough, the tennis ball will slow down a bit, but it'll keep on going off into space and it'll escape the Earth's gravity. Clearly, I can't throw it that fast. So what determines whether the tennis ball flies off into space or falls back down is the mass of the Earth, how much mass there is in the Earth, how much gravity is pulling back on the tennis ball. So too it is with the universe. If the universe has a lot of matter in it, then it has enough matter to pull back on the expansion of the universe. So even if the universe is expanding now, eventually it'll halt its expansion and collapse. On the other hand, if the universe has very little matter in it, then the expansion of the universe will continue forever. So that was realized in the 1930s. Forever. Forever. And I'm going to come back to that, but please ask me about that, because that's a very critical point. There would be nothing to stop it. Now, if you find that unsatisfying, I think you're not alone, but the universe would start at a particular instant, which is the Big Bang. Like that instant, you could calculate, if you knew how to, it happened, a certain number of seconds ago, and you could put decimals on those seconds. So there's a precise instant in time when the universe started its expansion. And yet, it could expand forever. It seems remarkable. Okay, so in the 1940s, it became clear that cosmology, the science of the universe, the origin of the universe, was a search for two numbers. One of those numbers was the age and the size of the universe. And the other number was the matter and energy density of the universe, which controls whether the universe will expand forever or else halt its expansion and start collapsing. And it was widely expected that this telescope, the Mount Palomar 200-inch telescope, when it was put into operation in the late 1940s, was going to solve both of these problems. It was thought that this telescope had the light-gathering power to see distant galaxies and by various means figure out what the answers were to these two questions. Over here you see a picture of Hubble taken in the 1930s standing in front of the Mount Palomar dome. By the way, how many of you have seen the Mount Palomar telescope? One person. It's quite something to see. It's a remarkable telescope. Does anybody here know Icelandic? This caption is apparently in Icelandic, and I don't know what it says, but I think you can guess. It probably says Hubble standing in front of the Mount Palomar dome, which is under construction or something like that. But anyway, it was widely expected that Mount Palomar and Hubble would solve these two problems. And this is a Time magazine cover from the early 1949, February 1949. I actually have this cover. My wife bought it for me for Christmas, actually, and it's now framed. But the Time magazine cover shows the Mount Palomar dome, and it shows this ghostly hand pointing up into the sky, and it shows a picture of Edwin Hubble. So Hubble never did live to see the fruits of the Mount Palomar telescope. He died in 1953 from heart disease, very young. He was in his, I think, he was in his mid-60s at the time that he died. So he never did see what Mount Palomar did. And so it's interesting to ask the question, what did the Mount Palomar telescope do? Well, 20 years later, there were two papers published, each one based on more than 1,000 nights of observing on the Mount Palomar telescope, which is a huge amount of telescope time. Two rival teams. Alan Sandage, who was Edmund Hubble's heir apparent, he was sort of anointed by Hubble as the person who would continue the program. Alan Sandage and two collaborators published a paper in which they concluded that the universe would halt its expansion and collapse within a few billion years. On the other hand, Jim Gunn and Bev Oak was a Canadian, and in fact he retired to Victoria about a decade ago and died just a couple of years ago. Gunn and Oak published a paper which said exactly the opposite. It said that the universe undoubtedly would expand forever. And that was back in about 1975. And basically the tools that they were using to try and figure out whether the universe would expand forever or halt its expansion, they were faulty. They just didn't work. And I would say that's where things rested for about 20 years. And so now we come to supernovae. And this is, I made this picture using the program Starry Night. Does anybody here use Starry Night?
Starry, starry night.
Yes, that's right. That's right, there's a song called Starry Night. But there's also a computer program that, like many other programs now, it can be used. It was one of the first. It can be used to simulate the sky and small parts of the sky on any particular night, going back, I think, 100,000 years and forward 100,000 years. This is what the sky looked like for an observer in China in the early morning of July 4th, 1054 AD. And you can see a few things that are familiar. Does anybody recognize this constellation here?
It's Orion.
Orion. How about this constellation here?
Gemini.
Gemini, that's right. And up there, Orion, that's right. And here's the Hyades that was being spoken about earlier, but the moon occulting stars in the Hyades. And in fact, you can see the moon in this picture. It's a crescent moon. And then here's Mercury. So this is July 4th, 1054. Now, with a little bit of artistic license, this is what the sky looked like on July 5th, 1054. And you can see that something has changed. And Chinese astronomers watched the sky every night and made a very detailed record of this. And this is the record here. This says, and I translate, in the fifth moon of the month Chi-ho. Actually, I'm kidding. I read the translation. I actually have the translation memorized. But this actually is an account of this exploding star, which appeared suddenly on July 5th, 1054 AD. It got brighter and brighter. Eventually it became quite a bit brighter than the planet Venus. It cast a shadow at night and it was visible during the daytime. And then it started to fade, and it took about a year to fade so that it couldn't be seen anymore with the naked eye. So that was quite remarkable, and it was something that Chinese astronomers realized was very special. And so they made a big deal about it. Surprisingly, it was either not seen in the Western Hemisphere, which is surprising because it's summertime, and in summertime the weather is good in Europe, for example, but no one in Europe seems to have remarked on this object. There may be a possible observation by Arabic astronomers. We're not entirely sure about that.
Is it that circular big one that looks like the sun?
Sorry?
That
That thing there?
Is that it?
That's it. That's it. It would have been a point of light. I had to make a disk to make it look brighter, but it was a point of light in the sky. But it was very bright, very bright.
And to the naked eye, could you see that?
That's what it would have looked like. Not in size, but in brightness. It would have been far brighter than anything else in the sky other than the full moon. The full moon would be the only thing brighter in the nighttime sky.
And so you're saying the size is immaterial?
Yes.
The brightness is the only thing that's important.
The brightness is the only thing that's important, yes. That's right. So this is a comparison of what happened back in...
Did you say it lasted for a year?
It lasted for about a year.
Wow.
Yeah. It faded, the record, and I could translate it, but I won't. It says it faded after about a year. Now, that's not exact, because what happened was the sun came in the way and it couldn't be observed for a while, and then finally when it could be observed again, it was gone. So it might only be 6 months, but at least 6 months, and possibly a year.
And there wasn't any kind of implosion or explosion?
It was an explosion.
Oh.
And in fact, this is what we believe happened. The star blew up and then shed a big cloud of gas. The cloud of gas in the 1940s was identified. This is the Crab Nebula. How many of you have seen the Crab Nebula through a telescope? Wow. It's actually quite, I find it quite hard to see. It's kind of low surface brightness. This is what the Crab Nebula looks like in a big telescope now, and that's the remnant of this explosion in 1054 AD. If you measure how fast these filaments of gas are moving, and then you calculate, how big the nebula is, sort of like you're driving from Victoria to Nanaimo, you know how far Nanaimo is, you know how fast you're going, you can figure out when you left Victoria, that kind of thing. And you can calculate that the explosion had to have happened around 1000 AD. So everything fits. And I just thought I'd throw this in. There's a pulsar near the center. This is a rapidly rotating neutron star, which is emitting flashes of optical radiation and radio radiation as well. So it can be seen with radio telescope. One interesting thing, I've never seen this myself, but this is a photograph from Chaco Canyon, New Mexico. And normally it's stated that it's only for sure that the Chinese observed this supernova. However, in this canyon in New Mexico, this is a place where First Nations peoples lived and flourished at this time. It was quite a moist climate, so it was easy to grow crops. There's a cave painting, and the cave painting shows a crescent moon, a bright star, and a hand symbol. The hand symbol is usually taken to mean a sign of something sacred. You quite often see this in rock paintings in the far north, for example. And you see the orientation of the crescent moon and the bright star is roughly correct for when the supernova went off. So it is believed that this is actually a First Nations representation of the supernova of 1054. And sure enough, it turns out that this cave was inhabited in 1054. So I think that's quite remarkable. Unfortunately, I don't believe you're allowed to go and see that. The cave is, or that area is off limits. Has anybody seen it? No? Okay, so the question arises, what are supernovae? I think I'm going to have to speed this up a bit, but basically there are two types of supernovae. There's this type of supernova here, which, as someone said, maybe it was you, is a kind of implosion that happens in the core of a massive star. And that implosion drives a shock wave through the star, and so the star explodes, and we see this tremendous optical event. That's one kind of supernova, and that is actually the most common type of supernova. It's called a core implosion or a core collapse supernova. But there's also this other kind of supernova that involves a white dwarf. And they're not quite as common, but they're still very interesting objects. What happens is a white dwarf either accretes material from a companion star, or two white dwarfs merge together. Either way, you've got white dwarfs involved in the explosion. And these things are supernovae too. They look a bit different from these things. These are called type 1A supernovae. Don't ask me about why 1A. These are called type 2 or core collapse supernovae. Well, why are supernovae interesting? Well, the first thing is that they're incredibly bright. They reach brightnesses which are 10 billion times, as much as 10 billion times the brightness of the sun, which is pretty incredible. That means that one supernova can outshine an entire Milky Way galaxy of stars at brightest light. Now, it doesn't always, but some supernovae could. Another thing about supernovae is that they're quite common. Now, by common, I mean that they're supposed to happen every 50 years in the Milky Way galaxy. And if you do the calculation, you can work out that in the observable universe, supernovae are going off at a rate of 10 per second. So 1 second, 10 supernovae went off somewhere in the universe, which is pretty amazing. So I would call that fairly common. I mean, they're not amazingly common, but they do happen, and they do happen quite a bit. If you stare at a patch of sky long enough, you're going to see a supernova eventually. Now, there is a little problem that we were talking about at supper. The problem is that in the Milky Way galaxy, supernovae are supposed to go off every 50 years, yet the last one that was observed in the Milky Way, does anybody know what it was? When it was observed?
1634 or something.
1604, that's right. 1604, it was Kepler's supernova. Johannes Kepler saw one in 1604. The amazing thing is, Tycho Brahe, observed one in 1572. Kepler observed this one in 1604, and then we haven't seen one since. So I don't know what's going on. I think we're overdue. I do know I shouldn't tell a story, but I'm going to anyway. When I was a graduate student, an unnamed professor was observing one night at the David Dunlap Observatory in Toronto. How many people have seen the David Dunlap Observatory? Quite a few people. He was observing one night with that telescope, and he looked over on the horizon and he saw a really bright star. And he thought, I wonder what that is. So he went to a star chart, and of course it wasn't there. So he immediately made this telephone call to Harvard, where there was a guy who was keeping track of things that changed during the night. And this nameless astronomer said, well, I think I've discovered the next galactic supernova. But it actually turned out to be the planet Mars. So, a slight embarrassment there. Anyway, so supernovae are interesting just because they're so powerful and so frequent. They're actually interesting things to study. This is a supernova that went off, was it last year? Or 2 years ago, thank you. In the galaxy Messier 82. Did anybody here see this supernova? Oh, yeah. Several people did, yeah. This was the closest type 1A supernova to go off in something like 40 years. So it was quite a remarkable event. Unfortunately, the galaxy Messier M82 is full of dust. And so because of that dust, the light from the supernova was obscured, it was made fainter. And so it doesn't appear as prominent as perhaps it should in this picture because it was absorbed so much. But still, it was a very important supernova for supernova scientists. Why are supernovae interesting? Well, both types of supernovae, both the white dwarf supernovae and the core collapse supernovae, are the sources of all of the heavy elements that we see around us. So this tabletop and a lot of the material in this phone and everything that we see around us, a lot of it was manufactured in supernovae, which is kind of remarkable that without those supernovae, the universe would be hydrogen and helium and nothing else, and we wouldn't be here. So, a lot of the stuff that's in our body was at one time manufactured in supernovae. And I think it's probably one of the most incredible discoveries of the past 100 years of physics, that all of the material around us at some time is processed through supernovae. Yeah.
Does it mean that those things turn energy into matter?
They don't turn energy into matter, but what they do is they slam together particles to build up heavier and heavier elements. They start off with hydrogen. Well, actually, in this case, they start off with things like carbon and oxygen, and then bang nuclei together to make ever heavier elements. And as they do that, energy is released because mass, a little bit of mass, is destroyed.
But in that picture, it obviously molecules are made out of atoms, and atoms are made out of particles, and particles are made out of blah, blah, blah.
Yeah.
And somewhere down there has to be some source of energy, right, to turn all those things to make all those things come to be, to combine and become, and combine and become.
Well, actually, once the matter is formed, which happened early in the Big Bang, so you could maybe blame the Big Bang for all the energy that eventually became matter. But then matter gets destroyed.
Yeah.
So going from helium to carbon, actually a small amount of matter is destroyed. And that is what powers the stars. And then going from, carbon and oxygen to iron is what powers
I see.
supernovae.
Yeah, so there's a, sort of a reciprocity in that picture.
Between matter and energy, you mean?
Yeah.
Yeah, back and forth, and that's what Einstein said, E equals mc squared. Another great thing that he did. Energy and matter are part of the same thing, part of the same fabric. And in quantum mechanics, we don't really differentiate between energy and matter. They're part of the same thing. They just have different appearances. Okay, the third thing is that supernovae are incredible sources of new physics. Now this shows two white dwarfs over a period of 1 billion years. The time is speeded up quite a bit here. Slowly spiraling together. They're spiraling together because they're losing energy, and they're losing energy from a process known as gravitational radiation. Anytime that an object falls into another object or orbits another object, gravitational radiation is emitted. And you could say, okay, so the Earth is going around the sun. Why doesn't the Earth merge with the sun? And the answer is, it will. Just come back in about 10 to 100 years. It's 1 with 100 zeros after. I don't know if that's the exact number, but it's some ridiculously large number. So the point is, the gravitational radiation is always being emitted, but for the Earth-Sun system, it's being emitted at about 60 watts, 60 joules per second, which is not very much energy for the Earth-Sun system. But in this case, over 1 billion years, two white dwarfs orbiting each other can merge together and produce a supernova. So these are great ways of learning about gravitational waves, and lots of other really good physics too. So that's one reason why they're interesting. And finally, if you go to Wikipedia and you type in extinction events, you're not just going to find out about the extinction of the dinosaurs 65 million years ago, which is what everybody talks about. You're also going to see a list of 30 other extinction events, 5 really big ones, over the past 2 or 3 billion years. Now, we think of the dinosaurs as having been extinguished by a meteor or a comet striking the Earth, possibly inducing other volcanic effects. We don't know about that. But it is possible that if a supernova goes off near the Earth, then extinction could follow. For example, the ozone layer would be destroyed. Perhaps even the entire atmosphere of the Earth could be ripped off. So this picture is not correct. If that's a supernova, the dinosaurs didn't have to worry, because that's not what wiped them out. However, other extinction events could, in the past history of the Earth, have been caused by supernovae. We don't know. And there's one more thing one more reason why supernovae are interesting. And to illustrate this, I'm going to show a picture. The picture is of a street light. Hopefully it has a cover on the top so the light goes down. And then you can see Venus, and you can see the moon. Now, if you were ranking these objects in terms of how bright they appear, clearly the street light is the brightest object in this picture. The moon is next brightest, and Venus would be the faintest of those objects. But if you were to rank those objects according to the power that they emit, the total luminosity that they emit, yeah, the streetlight is negligible. Now, if you were at the distance of the sun, you would never see that streetlight. The moon is quite powerful by reflected light, mind you, but it's not nearly as powerful as the reflected light that Venus gives off. If you just measure it in power, joules per second or something like that. And so these objects are not the same. They're very, very different, and I think that's completely obvious to everybody. But there do exist some objects which are the same everywhere in the universe. They give off the same amount of power, and we call them standard candles. For example, these candles are identical candles, and you can see how, when we look at them, as they get further and further away, they get fainter and fainter. And so if you can measure the brightness, the apparent brightness of one of these candles, you can tell how far away it is. And that is a very important technique that we use in astronomy. But of course, to use that technique, you first have to figure out what is a standard candle. Well, it turns out that supernovae are standard candles. Specifically, this type of white dwarf supernova that I've been talking about. And as you look at them further and further away, they get fainter and fainter. Conversely, you can look at those supernovae, figure out how bright they are at maximum light, and figure out from that how far away they are, to within about 5%. In addition, you can see them to very large distances because they are so incredibly bright, so incredibly luminous. And so what that means is you can measure distances in the universe out to billions of light years with these supernovae. I do have to add that, quietly, I have to add, supernovae are standard candles at maximum light under certain conditions. And I don't want to go into that anymore. You could ask me about it afterwards, but they are a sort of standard candle. And in fact, they are the best standard candle, useful for measuring distances that we've ever found. And this is what Hubble and Alan Sandage and Jim Gauss-Bevel were missing in their work when they tried to figure out the nature of the universe. They didn't have a good standard candle. We have one now, which is supernova. So I'm going to tell you now about a project I was involved with. In fact, it continues on. It's called the Supernova Legacy Survey. It was conducted at Canada, France, Hawaii Telescope, which you see here. And it was conducted with a gigantic digital camera. It's like your camera or an iPhone camera, except instead of being that big, it's about that big. And it's cooled, so it's very, very sensitive. Here it is here, shortly after its manufacture in 2002. So we put that camera at the focus of the Canada, France, Hawaii Telescope. And then it's quite simple actually. We were allocated 500 nights of telescope time over 5 years. And we just, every 4 nights, we'd observe the same fields in the sky. That was 4 separate fields, 4 1² degree fields in the sky. And we just look at them over and over again and discover a supernova. And it worked fantastically. We discovered 2,000 supernovae. 2,000 type 1A supernovae. And of those, we kind of hand cherry-picked 500 of them for further study because they looked to be really good supernovae.
Did they stay on a string like a bee? I mean, a bead on a string?
Well,
Does that, I mean, obviously they have to move to implode or explode or whatever, but when you're studying them, do they line up in strings like the pictures?
they don't really line up in a string, but you know, you're looking at an area about 1 degree by 1 degree. That's 4 times the size of the full moon, roughly, on the sky. And somewhere in that picture, a supernova is going off. So it's in the same general direction. And you know, like I showed you, the distant ones are really faint, and the nearby ones are quite bright. And by measuring how bright they are, you can figure out how far away they are. This is an example of one of the supernovae we discovered. This is a galaxy at a redshift of 0.3, which means you're looking back probably about 3 billion years. And this supernova exploding over a period of months is this explosion actually happened 3 billion years ago. So that's kind of remarkable. We're now picking it up. Now this galaxy, it's kind of fuzzy because the galaxy is so far away, but you can clearly see the supernova rise up in brightness and then fade over a period of months after that. Here's one of our 2,000 detections. And so these are 3 pictures. The first picture here is what a tiny, tiny part of our picture taken with the telescope looked like on March 10th, 2004. And this is a field, I can tell from this designation here, D2. It's in a little field in the constellation Leo. Okay, so this object, redshift 0.83, that means we're looking back 7 billion years. So what we're observing here happened 7 billion years ago. For reference, the universe is thought to be 13.72 billion years old. So you're looking back more than half the history of the universe. And actually, you're looking back to a time when the universe was quite different from the way it is now. Now, the confusing thing about this picture is that what is black in this picture is light. Like this is the dark night sky, and these 3 things here are galaxies. And because they're so distant, they look kind of fuzzy, even with a big telescope. This is what everything looked like on March 10th, and this is what the same field looked like a year earlier. And it's not quite as noisy for various reasons I can go into. Now, to you and I, when you look at those pictures, they don't look very different. This one's noisier, but you basically see the same 3 objects there. But there is a difference, and I wrote the software that analyzed these pictures. That was my contribution to this project. And when you subtract this picture from this picture, what you see is galaxies cancel out because they haven't changed. But one little object there is a bit brighter. And if you have a good imagination, you can sort of see it right up there. There's a little bit of an extension to that galaxy. So this is a supernova, 10 billion times the luminosity of the sun, that blew up. Well, it blew up 7 billion years ago, but we observed the light from it in 2004, in March. Now, you might not believe that, and sometimes I look at this picture or pictures like this of the other 2,000 supernovae, and I think, get real. Can you believe that? But in fact, you can. And it just so happened, I picked this supernova because at the very same time, the Hubble Space Telescope was observing this field, these galaxies. And now you can see things much more clearly with the Hubble Space Telescope. There are the 3 galaxies, and sure enough, there's the supernova right there. So the software really works. So I'm not just making this up. Okay, so I think we're getting kind of close to where I want to get. There are 2 measurements that we want to make with these supernovae. One is brightness, the other is redshift. Let me talk about brightness first. How bright the supernova appears tells you how far away the supernova is and how long light has been traveling from the supernova to us. And that brightness depends in turn on the topology of the space of the universe, whether the universe is incredibly curved in space or whether the universe is kind of flat in space, so light travels in a straight line. And this is sort of what Einstein was talking about, the overall curvature of the universe. So that is one measurement that you can make just by measuring the brightness of a supernova. There is a second measurement that you can make, and that measurement is the spectrum of the supernova. You take a spectrum of the supernova with a Gemini telescope, in this case, and what happens is the supernova light is stretched out by the expansion of the universe. So, the light starts off a wave like that, and then as the universe expands, the light becomes longer in wavelength. And so by measuring how much the light has been stretched, that is the redshift of the light, you can actually figure out how big the universe was when the light was emitted. If the light is being expanded, the waves are being pulled apart by a factor of 2. What that means is the universe was half its present size when those light waves were emitted. It's a very simple concept.
You talking about the frequency and wavelength?
Yes. It's sort of like the Doppler shift, except it's not a Doppler shift. It looks like a Doppler shift, but it's not a Doppler shift. It's, people talk about galaxies moving away from us at half the speed of light, but really what's happening is space is expanding and stretching the light. And it's different. It's quite different. Okay, so what we did was we observed, this is what we expected to see. Here are a bunch of supernovae. From the wavelengths of light, we get the size of the universe. From the brightness of the supernova, you can tell when the light was emitted and how long the light has been traveling. And we expected to see a curve something like this. It's a curve where the universe in the past was expanding, but you can sort of see how it's slowing down. And that's what we wanted to see. And remember, it's the tennis ball. The tennis ball goes up, and gravity pulls it back down, or at least, at the very least, slows the tennis ball down. The gravity of the universe is slowing the universe down. Okay, so...
Excuse me.
Yeah.
Okay, because this is kind of fairly critical here. So
Yeah.
the size of the universe you've got by how much the wavelength has changed.
Yeah.
But how do you know the time? How does that?
Because by measuring the brightness, you can measure the total path length of light between the supernova and us.
Oh, the time that it looks, okay.
Yeah.
So it's that far away,
Yeah.
basically, in
Yeah.
effect. Okay.
Yeah, it's a number of light years, if you like.
Okay.
But it's a question of whether the light years went like that or whether they went like that. So, they're two different universes, I guess.
Yeah.
Yeah.
Okay.
So that distance then tells you how long the light has been traveling, and that is, in other words, how much you're looking back in time to see a certain supernova. So we're measuring time backwards from here. Okay, so what did we actually see? What we actually saw was this, totally different. Here's the universe. The universe is getting bigger. It's slowing down as we expected. But then what we actually saw was the universe turning around and actually starting to go faster and faster and faster.
To what?
The universe, yeah, well, thank you for expressing surprise. It surprised the hell out of everybody. So the universe started to slow down. But 5 billion years ago, I don't know why, it started to speed up again. And that's, it's slowing down, slowing down, slowing down. And now it's curving up, so it's going faster and faster and faster. The universe is accelerating. That's as weird as taking this tennis ball, throwing it up in the air, and seeing the tennis ball take off and go faster and faster and faster. Isn't that weird? You would not expect that. Sorry?
The opposite direction that it was going.
Yeah. So completely in the opposite direction. What this means is Einstein was right after all. There is a large-scale repulsive force in the universe. Remember that funny symbol, that lambda, that cosmological constant, that he introduced to stabilize the universe? Actually, that exists, and it's pushing the universe apart. We call it dark energy. Okay, we weren't the first people to discover the acceleration of the universe. This team, these two teams actually, Adam Rees, Brian Schmidt, Saul Perlmutter. Saul is actually part of the Supernova Legacy Survey. But these three people got the Nobel Prize in 2011 for the acceleration discovery. But what we discovered was more than just the acceleration with our data. They only had something like, these guys had 15 supernovae. Saul had something like 30 supernovae to work with. But we had, 1,000, well, I guess we analyzed 500 supernovae. And with 500 supernovae observed more carefully, what you can tell is whether the nature of the acceleration that you see is like Einstein's cosmological constant. And that's what we discovered, that really the acceleration of the universe is exactly what you expect from Einstein's cosmological constant, which is quite remarkable. So here you have source of gravity equals curvature of space. I showed you that. Einstein put in the lambda term, which is a large-scale repulsive force. We call it dark energy. And Einstein was right after all. So, it wasn't Einstein's biggest blunder. It was, in a way, his greatest discovery. So, matter and energy in the universe, a strange group. Has anybody seen this movie? It's a terrible movie, and I would not recommend it. But here is matter and energy in the universe. We have 5% normal matter. We have 25% this stuff called dark matter. Maybe you've had talks on that. It's stuff that fills the universe. It passes through the Earth, passes through the sun, passes through us. Most of the gravitating matter in the universe is dark matter, not normal matter like what we're made of. But here we've got 70% dark energy, which is something totally different. But its matter equivalent is greater than that of dark matter or normal matter. It's truly phenomenal that we live in a universe where 95% of the universe is made out of stuff that we don't know what it is. We have no idea what it is.
And that is dark energy? No.
Sorry? Dark energy. Dark energy and dark matter too, but I want to be very clear about this. Dark matter and dark energy are not related. They have the word dark in them, but that's the only thing they have in common. And I think I have a quotation coming up. Well, I'll come to the quotation in a minute. What is the dark energy? Here's part of a review paper on dark energy, and there'll be an exam quiz after the lecture is over, so read this very carefully. But the basic point is that about once per day, I've actually checked this, and it's still true, that if you go online, we have a preprint server where all the papers that are going to be published appear online before they appear in the journals. And there are about 100 papers a day that come out in various fields. And there's at least one paper a day about the nature of dark energy. So, probably every one of them is probably wrong. But, people continue to think up mechanisms for the dark energy.
Why is it called dark?
Because you can't see it. But it's a terrible name for it because it's nothing like dark matter. And, it just gets people confused when you talk about dark energy.
It sounds ominous.
Well, yeah. One person said, that sounds like my mother-in-law. But it's dark energy. Oh, let me tell you something else very, very unusual about dark energy. Now, this should really make you think. You take a cubic centimeter of the universe, and you measure, if you could measure the amount of dark energy in it, well, it would come out to a number like 10 to the minus 8 electron volts or something like that. So you wait, there's a certain amount of energy in that cubic centimeter. So then you wait, I don't know, 1 billion years or 2 billion years, and so meanwhile, that cubic centimeter has expanded. I don't know by how much, but it will have expanded because the universe is expanding and accelerating. And you come back, and now you take a cubic centimeter and you measure how much energy is in it. How much do you think? It'll be less than a cubic centimeter because the universe is expanding. Less than that amount because the universe is expanding. But it turns out that this kind of dark energy, the cosmological constant, you'll get exactly the same amount of energy in that cubic centimeter. So if you want to know what that means, it means that the universe is manufacturing dark energy. Energy is not conserved. If you come back 10 billion years from now, the universe will have 8 times more dark energy in it. Where does that energy come from? I have no idea. It's absolutely crazy.
Was one explanation that I saw was that the vacuum energy is fully accounted for perhaps by pair production, and so that generating some form of energy, and it can't be measured on a local scale, but because of the huge size of the universe, it has the energy factor comes into play as dark energy on a much larger scale, and so is what I read. Does that make sense?
It doesn't make sense to me, just like all of the other explanations don't make sense, but you might be right, but I'm just not sure about that at all. Yeah.
Okay, a long time ago, as in about like 15 or 16 years ago, before they discovered these supernovae, okay, there was a lot of talk in sort of the balance of energy and matter and dark matter in the universe. It had to end up being sort of the critical mass, just the right amount to separate, an eternal universe from a crunching universe. Okay, am I right? Okay. And so it was, and so there was, and there was supposed to be this percentage of regular matter, and this percentage of dark matter, and this percentage of something else. What has become of that? Now that we're manufacturing energy, the whole idea of critical mass and energy seems to have been completely thrown out, but I've never actually heard what has become of that idea.
Okay, so that's a good question. You're absolutely right that 15 years ago, before all this happened, or maybe a bit more, theoreticians used to argue for what we called an omega equals 1 flat universe, where it was exactly the critical density, exactly in the middle of expanding forever or eventually starting to collapse. And they used to argue for that primarily on aesthetic grounds. There was no other reason to think of that. What we have now, and thank you for bringing this up because I meant to mention it and I forgot. You add up the dark matter, the normal matter, the dark energy, and you end up with exactly a critical universe. Space is flat to within 1%. It is now being measured using the microwave background, the cosmic microwave background. Space, the topology of space-time is exquisitely flat. Now, we can't tell the better than 1% right now, but that's pretty flat. And so for all these components to add up to a universe that is almost exactly flat is truly remarkable. There are theories that would explain that, but I'm not sure what to make of them.
But what's that mean, the critical density? What would that mean if we're getting more and more of one of the components? Like the original idea was that there was a certain fixed amount of matter and whatever energy that made this omega 1 up there.
Yeah.
Okay. how can that be now that we're getting like 8 times more? You know.
Well, you're right, except the universe is expanding, and so it takes more, as time goes along, it takes more and more dark energy to make the universe flat.
Okay.
So it's kind of a
So
compound.
the flat idea is kind of stuck with us.
Yes, yes,
Okay.
that's right.
Okay.
Fills it in as it goes.
Sorry?
It kind of fills it in as it goes.
Yeah, that's right. Yeah, it's, yeah.
My question is about the whole thing.
So mine too, actually.
I've got a lot of questions about that.
It's, you know, we're looking at these pictures, and for example, the curved one that then it had a different curve in it,
Yeah.
and the what are they called, the supernova,
Mhm.
they look like they're strung on a string, and the picture shows that they're in an order,
Mhm.
right? So isn't that within that order, isn't there clues to what those supernova, are those supernova actually connected to the next one in the row?
No,
And how they,
no.
and do they move from their positions around and not navigate, but just drift, or?
No, they don't. So the supernovae that we observe, the 2,000 supernovae over 7 or 8 years, I guess, are completely, they don't know about each other.
Independent.
They're completely random. So this, you know, we're observing probably 1 million galaxies in our picture. And over that period, you know, it's just random galaxies. It just happened that stars were in the right phase of evolution to trigger a supernova.
So
And you're asking about something, this is actually the thing that I study, because I'm really interested in the cosmology, but I think we're at a dead end right now, as I'm going to say in a moment. I'm really interested in the supernovae themselves, and that's what I'm starting to research more and more.
Those ones that look like they're on a string, that's just a way of looking
It's just-
at them.
Yeah, it's just a
And
way of
and
looking.
those, even though they seem to have a curved connection all the way
Mhm.
along, those are taken this way from here and that,
Yes,
there and
that's
there.
right.
And then you just put them there because they show resemblances to each other, or
Yes,
that sort of thing.
because they show resemblance to each other, and because the supernovae are at a wide range of distances. You know, it would be interesting to make a movie of flying through this field, and, you know, at, I don't know, billions of times the speed of light. Then you'd start off 1 billion light years away, and you'd see supernovae going off 2 billion years, 3 billion years, and so on. And supernovae would be going off all around you. And those supernovae wouldn't know about each other. They're just going off. But the string idea, you know, it's a little confusing, but I just meant to illustrate the fact that there's a wide range of distances. You're looking at one field in the sky, but you're looking through that field and seeing a wide range of distances. Yeah.
Dark energy is really just a mathematical concept that explains some phenomena. We haven't actually able to measure.
I mean, like in the lab.
Yeah, like a dark, and when going to, do you think we'd ever be able to tap into that?
Well, that's a really interesting question. Could you ever tap into dark energy? I don't think you could. But could you measure it in the lab? There is actually an experiment that has been proposed that supposedly could detect a tiny amount of dark energy. It's a solid state experiment with, you know, superconducting whatever, so I don't know much about that, so I can't assess whether that experiment would ever work. But people are starting to talk about that. But I did want to say, I have a whole bunch of slides here which I'm going to skim over as time is marching along. What is the dark energy? I think there are 2 possibilities. One of the possibilities I've already mentioned is some sort of new physical component. And I talked about the cosmological constant. There are these other models that were mentioned in this article that is going to be examined on. And those articles, those things, I think are being ruled out now. And I think we're stuck with the cosmological constant, which is this weird dark energy that creates itself as the universe expands. But there could be other physical components, and I think the way we could understand those is if we were able to measure the amount of dark energy as a function of time, as a function of look-back time directly. And there are actually ways of doing that using supernovae. And the next generation of telescopes, like the 30-meter telescope and others, will perhaps be able to do that.
Okay, when you had your S-curve showing the, and you said there was a change about 5 billion years ago,
Yeah.
was the amount of dark energy 5 billion years ago still 70%?
It would have been less, because the amount of dark energy is increasing with time.
Okay.
Yeah. And so what happened was, the dark energy started off very low, and of course matter dominated. But about 5 billion years ago, the effects of dark energy and matter crossed. The matter started to gravitate less because the universe is expanding, but dark energy started to push apart more because of the repulsive force. And that's what's been going on for the last 5 billion years. And if you come back in 50 billion years, the universe will be going like crazy, flying apart, if this is correct. Yes?
Can pure vacuum exist or possible?
Say that again?
Pure vacuum, is it possible?
Well, I think what this says is a pure vacuum is not possible because all vacuum contains this energy,
Right.
which is part of the vacuum. So in that sense, it's not possible. Yeah. Yeah.
The rate of increase of dark energy, is that a straight line or is it an exponential function?
If we're right in our measurements, we can say very precisely how the amount of dark energy increases. It increases as the volume of the universe increases. And that's it. We can tell that right now to within about 5%. So it can't deviate from that by more than 5%. Okay, I just want to mention the other thing that the dark energy could be, and I haven't mentioned this at all up till now, and people tend not to talk about this. But I want to say that it could be that rather than a new physical component in the universe, it could be a new physical law. That is, maybe we could take general relativity and tweak it a bit or change it a bit. Just like we had Newtonian gravitation for hundreds of years. And then we discovered that really, although Newtonian gravitation works very well in the solar system, general relativity is really needed when you're dealing with massive compact objects and black holes and things like that. But maybe there's a next step. There's a new generation of models that are required to explain gravity. Maybe it has something to do with something physicists call quantum gravity. Maybe gravity has to be unified with quantum mechanics in some way. That is way beyond my pay grade. I don't know anything about that. But people have talked about that for decades, and no one has made any progress with quantum gravity. But it could be that our fundamental physical laws are the source of what appears to be the acceleration of the universe. I think a good way of summarizing everything is this guy, Rocky Cole, a very famous theoretical physicist. And I was at a talk that he gave about 10 years ago, and he said, on a good day, I can think of 3 or 4 plausible candidates for dark matter. The same cannot be said for dark energy. And that's as true today as it was in 2004. Dark matter, we don't know what it is, but we see its effects. And people, for example, at the Large Hadron Collider, if you look at today's Globe and Mail, was it today's? I think it was today's Globe and Mail. There's a big centerfold on perhaps the Large Hadron Collider actually being able to detect dark matter particles. And you can certainly think of a few candidates for dark matter particles. But the whole dark energy thing it's crazy. So to conclude this talk, just have a few conclusions. The universe is expanding. We've known that since 1929, Hubble's and Vesto-Slipher's discovery. We expected the universe to be slowing down its expansion because of gravity, but it's not slowing down, it's speeding up, which is bizarre. So what we say is the universe is filled with a mysterious substance, which we call dark energy, that causes this acceleration. What it is, why it's there, we don't know. I think it's fair to say that this is one of the greatest mysteries in physics and astronomy in the past century, and I don't think it's going to be solved anytime soon. And the final conclusion is, stay tuned.